April 8th, 1943. South Pacific, near the island of Buka. The captured aircraft stood motionless on the coral runway, its green paint shimmering beneath the morning sun. Around it gathered a circle of American pilots and engineers, their faces a mixture of curiosity and disbelief. The airplane, once feared for its long reach and precision raids, was a Mitsubishi G4M, known to them as the Betty. It had been forced down nearly intact after anti-aircraft fire crippled one engine. Now, in the clear tropical air, the Americans could finally examine the machine that had struck so many Pacific bases and sunk so many ships. Lieutenant Colonel William McCoy, an ordnance officer from the 13th Air Force, walked slowly beneath the slender fuselage. His eyes followed the smooth aluminum panels, noting the absence of armor plate and the thinness of the skin. He tapped the metal with the handle of his flashlight. It rang with a brittle sound. Beside him, Captain Al Curtis from the 70th Bombardment Squadron bent to inspect the landing gear wells. No protection, not even rubber liners, he muttered, astonished. McCoy glanced toward the wing roots, then at the open bomb bay, large, clean, almost delicate in construction. Every line of the aircraft spoke of speed and range, yet it felt fragile, like something built to be admired rather than endured. The Americans knew the Betty's reputation. Since 1941, it had carried Japan's war across thousands of kilometers of ocean, bombing Wake Island, striking at Darwin, launching the torpedoes that sent the British ships Prince of Wales and Repulse to the bottom. Its long, elegant wings and twin engines had given it a range no Allied medium bomber could match. Yet now, standing close, they understood the terrible price Japan had paid for that range. There was no armor around the crew positions, no bulletproof glass at the cockpit, and, most shockingly, no self-sealing fuel tanks. McCoy ordered a panel removed from the port wing. The mechanic slid back the riveted aluminum cover to reveal one of 8 large fuel tanks, simple, unprotected, wrapped only in thin metal and fabric. A single incendiary round could ignite the entire supply of 4,180 liters in seconds. He stared into the cavity, momentarily speechless. They built a bomber that flies like a dream but dies in a spark, he said quietly, his voice flat with disbelief. Around them lay fragments of Japanese equipment, maps still pinned to the navigator's board, a logbook half filled with kanji characters. The air inside the fuselage carried the faint, sweet smell of gasoline. One American pilot, running his hand along the fuselage, remarked that it felt more like a racing yacht than a warplane. Every structural decision favored lightness over safety. Even the control cables were thinner than standard U.S. specifications. In that moment, the contrast between two engineering philosophies became visible under the tropical sun. The Japanese had built a machine to cross oceans. The Americans had built machines to survive combat. What looked like elegance was, in truth, a form of calculated fragility. The Betty was fast, efficient, graceful, and fatally vulnerable. The captured bomber would soon be dismantled piece by piece, its secrets recorded in the notebooks of American technicians. Yet what astonished them most was not what they found, but what was missing. That realization, so simple, so devastating, would echo through every report that followed, marking the beginning of a deeper inquiry into how Japan's pursuit of range had turned into a design philosophy of self-destruction. The Betty had not been born from recklessness, but from geography. No other nation faced distances like Japan. Its empire stretched in thin arcs across the Pacific, from Kyushu to Truk, from the Dutch East Indies to Rabaul. Each conquest demanded aircraft that could leap thousands of kilometers between island airstrips or aircraft carriers. In 1937, the Imperial Japanese Navy issued a specification that seemed impossible: a land-based twin-engine bomber able to fly 5,000 km, carry an 800-kilo bomb load, and cruise faster than the fighters escorting it. Engineers at Mitsubishi accepted the challenge with patriotic pride. Chief designer Kiro Honjo understood that such range could only come from radical lightness. Every kilogram of armor, every self-sealing fuel layer, every redundant control cable was an enemy of distance. When work began on the prototype G4M in 1939, Japan's war with China already showed the need for a bomber able to reach distant ports and flee before interception. Honjo and his team studied the earlier G3M Nell, which had demonstrated Japan's doctrine of aerial reach: long, thin wings, minimal structure, and enormous fuel volume. The new design would take that philosophy to its extreme. Japanese naval aviation at the time was guided by Admiral Isoroku Yamamoto's vision of decisive strikes delivered by fast, long-range aircraft. He believed Japan's only chance against Western powers lay in surprise attacks before industrial might could react. The Navy Air Technical Arsenal at Yokosuka translated that strategy into engineering: range first, survivability second. Test pilots accepted the risk. For them, duty outweighed armor. When the first G4M flew on October 23, 1939, it exceeded expectations. At 427 km/h top speed and nearly 5,000 kilometer combat radius, it was unlike any bomber in the world. Even the new American B-25 Mitchell could barely reach 2,600 kilometers with half the payload. The Mitsubishi's designers had achieved the impossible: an aircraft that could strike across oceans without refueling. They had also created a weapon that would ignite if touched by a tracer fire. The Navy's enthusiasm blinded it to danger. In testing, engineers warned that the aluminum skin deformed under heavy G-loads, that fuel vapor leaked through seams, and that no self-sealing tanks meant even a single hit could doom the crew. The response from command was curt: range is armor. In the logic of 1939 Japan, offense equaled protection. An aircraft that could reach the enemy before being seen would not need armor at all. When war erupted in December 1941, the Betty embodied that logic perfectly. The first combat missions against Clark Field in Hong Kong confirmed its promise. Flying from Formosa, Betty struck targets over 1,500 kilometers away, destroying American and British aircraft before they left the ground. On December 10, 1941, 22 G4Ms from the Kanoya and Takao air groups attacked the Royal Navy's Prince of Wales and Repulse off Malaya. Skimming the waves at 30-mile altitude, they launched Type 91 torpedoes that tore both battleships apart. The attack, immortalized in Allied memory, made the Betty legendary overnight, but success concealed fragility. Even in those early victories, the cost in aircraft and lives was mounting. Over Malaya, flak bursts ignited leaking fuel lines. Several Bettys exploded in midair before dropping their torpedoes. The Navy called it honorable combustion. Pilots accepted death as a byproduct of range. They were told that self-sealing tanks would add 500 ku, reducing mission radius by 400 kilometers, unacceptable in Japan's strategic calculus. By mid-1942, the G4M had become the backbone of Japan's maritime strike wings. Units based at Rabaul, Truk, and the Marianas used it to patrol seas larger than Europe. Its crews learned to fly with the knowledge that a single bullet through the wing could turn the aircraft into a fireball. Survivors described the eerie silence before the flames, fuel vapor igniting so suddenly that gunners vanished into flashes of light. Despite these losses, production accelerated. By late 1942, over 600 airframes had rolled from Mitsubishi's Nagoya plant, each one crafted with the precision of a racing plane rather than the ruggedness of a bomber. The Allies noticed. Reports from surviving pilots at Guadalcanal described Japanese bombers that burned like paper lanterns. American interceptors soon learned to aim for the wings. Even a burst from a single .50 caliber gun could reduce a formation to smoke trails. Yet intelligence officers remained puzzled. Why would a nation capable of such sophisticated design ignore basic protection? The answer lay in resource arithmetic. Japan's pre-war aircraft industry operated under strict weight limits dictated by aluminum scarcity. Strategic planners prioritized naval shipbuilding, leaving aircraft designers to shave grams wherever possible. Armor plate, self-sealing rubber, and heavy structural reinforcements were luxuries reserved for experimental fighters or prototypes. The Navy's procurement board believed every kilogram saved on each bomber meant another few kilometers of range. To question that logic was to question Japan's grand strategy. Still, not all officers agreed. Commander Takuzo Matsumura, an engineer with the Yokosuka Air Arsenal, submitted a report in 1941 recommending partial fuel protection. His calculations showed that reducing range by 8% could double crew survival. The proposal was dismissed as defeatist. After the fall of Singapore and the early Pacific triumphs, no one wanted to argue with success. As 1943 began, that success was unraveling. Allied radar, faster fighters, and improved anti-aircraft guns turned the Pacific into a killing ground for unarmored bombers. Losses over Guadalcanal and the Solomons exceeded 60% in some squadrons. The once feared G4M became known among its own crews as the Type 1 lighter. Mechanics joked grimly that it came equipped with wings and a match. When one of these bombers crash-landed intact on Buka and was captured by U.S. forces, the discovery promised answers. For months, intelligence officers had studied combat reports that defied logic. How could an aircraft with such long range also be so easily destroyed? Now the Americans would learn firsthand. Engineers prepared to disassemble every system, record every dimension, and test every tank. What they would uncover inside the slender fuselage would astonish even seasoned experts, because behind the Betty's elegance lay the pure expression of a nation's strategic desperation, a machine that embodied Japan's belief that reaching the enemy mattered more than surviving the encounters. It was not simply a bomber. It was a philosophy made of metal and fuel, soon to be understood in all its tragic perfection. When the American engineers began their formal inspection of the captured Mitsubishi G4M, they approached it as they would a scientific specimen. Every rivet, valve, and fitting recorded, every material sampled. The aircraft had been repaired enough to allow ground testing. Under the supervision of Major William McCoy, the technical intelligence team from the 13th Air Force began to strip away its skin panel by panel. What they found inside stunned even men who had spent years studying Japanese aviation. The G4M's design philosophy was uncompromising. The airframe was built almost entirely from lightweight aluminum alloy, polished and thinned to the edge of fragility. The empty weight registered only 6,541 kg, nearly a ton less than a comparable American B-25. Every structural element seemed pared down to the minimum. Bulkheads reduced to latticework, longerons drilled with lightning holes, spars that looked almost too slender to bear flight loads. In the pursuit of range, Mitsubishi's engineers had trimmed the aircraft to its bones. The most remarkable and fatal feature lay in the fuel system. The Betty carried 4,180 liters of gasoline distributed across 8 main tanks, 4 in the wings, 2 in the fuselage, and 2 smaller reserves near the center section. Each was built from thin sheet aluminum lined with cellulose lacquer. There was no protective rubber, no self-sealing compound, and no armor plate between the tanks and the crew compartments. To save further weight, the tanks were vented directly to the atmosphere through small tubes along the wings. It was a perfect design for range and for fire. Major McCoy recorded in his technical report, "Every structural decision in this aircraft appears intended to reduce weight regardless of combat survivability. The wing tanks can be pierced by a screwdriver. Vapor concentration in the fuselage is dangerously high. A single tracer round would ignite the entire supply." His notes included a simple calculation. The gasoline aboard the Betty weighed nearly 3,600 kg, more than half the total loaded weight. The bomber, in essence, was a flying fuel container with engines attached. Even the crew accommodations reflected this obsession with range. The pilot's seat offered no armor plate. The dorsal and ventral gunners sat within transparent domes that provided excellent visibility, but no protection from fire or shrapnel. The control cables ran exposed along the fuselage walls. In some sections, American engineers found that electrical wiring shared conduits with fuel lines, a hazard unthinkable under U.S. standards. The radio equipment, though advanced for its time, was mounted on bare racks without shielding. When a bullet struck the fuselage, it could travel unimpeded through metal, wires, and men alike. The engines were twin Mitsubishi G4M 14-cylinder radios producing 1,530 horsepower each. Smooth and reliable, they gave the G4M its distinctive high-pitched drone and remarkable fuel efficiency. Each power plant drove a three-bladed, constant-speed propeller designed for endurance rather than climb. The cooling ducts, minimal and closely cowled, reduced drag but made overheating common during long ascents. The exhaust stacks were unshielded, leaving bright trails visible for kilometers at night, one more compromise made for performance over safety. The Americans noted the bomber's aerodynamic elegance. Its 25-meter wingspan, thin section, and clean fuselage lines gave it exceptional lift-to-drag efficiency. At cruising power, it consumed barely 360 liters of fuel per hour, almost half the rate of an American B-26. This allowed the Betty to reach a maximum range of 4,900 kilometers, extraordinary for a twin-engine aircraft. But that efficiency depended entirely on its fragility. Adding armor or self-sealing tanks would have destroyed the very quality the Navy prized most. To test structural strength, the Americans performed static load trials on detached wing sections. Under simulated stress, the aluminum spars began to deform at only 85% of equivalent U.S. specification limits. Yet within its intended envelope, the aircraft performed flawlessly. Test pilot Captain Al Curtis later wrote, "The Betty handled beautifully, light on the controls, responsive at any speed, gentle in turns, but it felt insubstantial. The cockpit shook under power like an eggshell flexing." The bomb bay told another story of compromise. Large and rectangular, it could carry either two 250-kilar bombs or one torpedo slung externally beneath the fuselage. The bay doors were thin magnesium alloy, easily warped by heat. On surviving combat examples, investigators found that leaking gasoline had dripped onto the torpedo release mechanism, creating explosions when electrical circuits shorted. The engineers concluded that even Japan's most successful naval strikes had been conducted in aircraft one spark away from annihilation. Inside the fuselage, evidence of rushed wartime production mixed with ingenious craftsmanship. Every component bore hand-stamped inspection marks. The riveting was precise, yet often irregular, suggesting assembly by skilled artisans rather than factory automation. This confirmed Allied intelligence that Japan relied heavily on manual labor rather than conveyor line production. The workmanship impressed the Americans, but also revealed why replacement parts were inconsistent. Each Betty was almost unique. Instrumentation was simple but efficient. Japanese metric gauges replaced imperial units, with altitude readouts in meters and airspeed in kilometers per hour. The engineers admired the clarity of the layout, fuel, temperature, and oil gauges grouped logically, but criticized the lack of redundant systems. A single electrical failure could render entire panels useless. When the Americans attempted to simulate battle damage, the results were catastrophic. A single 50 caliber round into the wing root caused instant ignition. The fire spread through the fuel vents and engulfed the aircraft in seconds. Even with onboard extinguishers, the heat became uncontrollable. McCoy's report stated bluntly, "The G4M offers no resistance to fire whatsoever. Structural aluminum collapses within 20 seconds of ignition." Still, the evaluation was not purely condemnation. The investigators recognized the elegance of Japanese engineering under constraint. They admired the efficient use of materials, the aerodynamic precision, and the simplicity of maintenance. The Betty was, in many ways, the logical product of an island nation fighting far from its shores with limited resources. It reflected both brilliance and desperation. By late May 1943, the technical report was complete. 52 pages of diagrams, fuel analyses, and performance charts. Copies were sent to Wright Field in Ohio and to the Naval Air Technical Center at Anacostia. The conclusion was unemotional, yet devastating. The G4M represents the triumph of range over survival. It is an aircraft designed for an early war environment where interception is rare. Against modern Allied defenses, it is functionally obsolete. That verdict marked the beginning of a shift in Allied understanding of Japanese technology. The Betty's lightness was no mystery of genius, but the result of impossible requirements imposed by strategy. The Americans had learned what the Japanese crews already knew, that their bomber was a masterpiece built for distances the Pacific no longer allowed, and that every liter of fuel inside it carried not only range but death. Production of the Mitsubishi G4M began quietly in 1940, inside the sprawling Nagoya works that had once built commercial transports. By early 1942, the plant operated day and night, its windows blacked out against possible air raids. Rows of bare fuselages stretched across the assembly bays like metallic fish, their thin aluminum skins gleaming under arc lamps. Each completed aircraft represented an astonishing balance of precision and compromise. Japan's industrial system, brilliant in design, fragile in scale, was straining to produce an aircraft that demanded perfection in every rivet. The first production variant, the G4M1 Model 11, entered service in mid-1941. It carried two Mitsubishi Kase 11 engines rated at 1,530 horsepower and could achieve 428 km/h at 4,500 meters. Range, with full internal tanks, reached nearly 5,000 km. Armament consisted of one 20mm Type 99 cannon in the tail and four 7.7mm machine guns in flexible mounts. The crew of 7 worked in cramped conditions, surrounded by fuel tanks that formed both floor and ceiling. It was a weapon designed for offensive reach, not for comfort or protection. Between 1941 and 1943, production expanded to satellite factories across Honshu and Kyushu. Nakajima and the 21st Naval Arsenal built components, while subcontractors in Osaka and Kobe produced engines, propellers, and fuel systems. Each airframe required more than 35,000 individual parts, many still hand-fitted. Output averaged only 20 aircraft per month in 1942, rising to 80 by early 1943. In contrast, the United States was producing 300 B-25s monthly and over 500 B-24s. Yet in Tokyo, these numbers were considered adequate. Quality mattered more than quantity until combat losses began to outpace production. As war expanded, Mitsubishi introduced incremental improvements. The G4M1 Model 12 added slightly more power, a dorsal turret, and strengthened spars. None of these changes addressed the bomber's central weakness. The Navy resisted any proposal that reduced range. Engineers argued for self-sealing tanks, pointing to reports of catastrophic fires over Guadalcanal. Their proposal would have added 400 kilograms and reduced range by 10%. Admirals dismissed the idea. If we shorten our reach, we lose the war. By 1944, the need for survival could no longer be ignored. American fighters, now operating from island bases within 800 kilometers of Japan's defensive perimeter, intercepted Betty formations before they reached targets. Losses exceeded one aircraft for every 2 missions flown. Engineers at Mitsubishi finally received authorization to redesign the structure. The result was the G4M2 Model 22, featuring Kase 21 engines and a modestly enlarged tail to improve stability. Performance improved slightly, maximum speed 437 km/h, sealing 9,000 unarmored, but survivability remained unchanged. The self-sealing tank system approved for development was still too heavy for operational use. A limited experiment with armor plate for the pilot and radio operator yielded disheartening results. The added 200 kg shifted the center of gravity aft, reducing climb rate and extending takeoff runs dangerously. Range dropped below 4,000 kilometers. Commanders rejected the modification after only 20 test flights. For Japanese naval doctrine, the Betty's range remained sacred, even if it meant sending crews on missions they could not survive. Production statistics from surviving Mitsubishi records reveal the scale of Japan's wartime strain. Between 1941 and 1945, 2,235 G4Ms of all versions were built. Of these, nearly half were destroyed in combat. By comparison, the United States produced more than 18,000 B-24s and 9,800 B-25s. The disparity was not only industrial, but philosophical. American bombers were designed for formation defense and crew protection. Japanese bombers were designed to reach the target at any cost. Late in 1944, the final variant, G4M3 Model 34, incorporated long-delayed safety improvements. Engineers finally installed self-sealing tanks and partial armor. The modifications reduced internal fuel capacity from 4,180 liters to about 3,400 liters. Maximum range fell below 3,500 kilometers, too short for many Pacific missions. Empty weight increased by nearly 600 kilos, erasing the aircraft's once celebrated agility. Pilots complained that the new Betty climbed sluggishly and required longer runways. In combat, its survival rate improved only marginally. By that stage, American air superiority made every sortie perilous. Even before these late changes, Japanese industry was collapsing. Allied bombing raids on Nagoya in late 1944 destroyed assembly buildings, machine tools, and skilled labor forces. Production dispersed into tunnels and rural workshops, where craftsmen worked by lantern light. Output dwindled to a handful of aircraft each month. Replacement engines were scarce, and aluminum shortages forced substitution with lower-grade alloys that corroded in tropical climates. Many of the final airframes never flew. Despite its fragility, the G4M remained central to Japanese strategy. It delivered the long-range strikes that defined the early Pacific War and later served as a platform for desperate innovations. Modified Bettys carried the Oka rocket-powered suicide bomb and served as motherships for special attack units in 1945. Their range, once a symbol of technical triumph, became an instrument of tragedy. American intelligence reports compiled from captured documents estimated that by mid-1945, fewer than 400 Bettys remained operational. Most were Model 22s, some retrofitted with partial armor, but still vulnerable to the smallest spark. Ground crews learned to refuel with extreme caution, grounding the aircraft with copper chains to prevent static discharge. Even so, accidental fires destroyed dozens on the ground. To historians and engineers alike, the production history of the G4M illustrates Japan's wartime dilemma in pure form: technical brilliance limited by material scarcity, and strategic ambition crippled by industrial weakness. Each aircraft carried within it the contradiction of a nation that could design but not mass-produce, innovate but not adapt. By the time the war entered its final year, the elegant bomber that had once terrified the Pacific skies had become a relic of a vanished strategy. The Navy still clung to its range tables and fuel calculations, but American radar, long-range fighters, and carrier task forces had rendered those numbers meaningless. The Betty had achieved everything its designers promised, except survival. The evolution of its production mirrored the arc of Japan's fortunes, rising precision, desperate improvisation, and eventual collapse. Each variant bore the scars of compromise, each improvement too late to matter. And as the last surviving airframes rolled from hidden workshops into the smoke of a dying empire, they carried with them the memory of an idea that had soared too far, an idea that range could substitute for protection, that distance could defeat inevitability. Combat would expose the contradiction that the factory reports only hinted at. The G4M's long wings and shimmering aluminum fuselage made it a predator at dawn and a funeral pyre at noon. When the Pacific War shifted south in 1942, the Betty became the spear of Japan's air offensive, fast, far-reaching, and fatally flammable. Its first sustained campaign came over the Solomon Islands. From bases at Rabaul and Cavite, G4M squadrons struck Allied positions on Guadalcanal, New Guinea, and the Coral Sea. Early missions achieved terrifying success. Flying from 2,000 kilometers away, they appeared without warning, their formation lines glittering in the morning sun. American ground crews described the sound, a high, synchronized hum like bees over the water, then the abrupt whine of descending torpedoes. Between August and October 1942, Betty sank or damaged 22 Allied ships, including destroyers and transports critical to the Guadalcanal campaign. But the cost was unsustainable. In the same 3 months, the 4th and 705th Kokutai lost more than half their aircraft. Pilots who survived reported fuel vapor filling the cockpit after minor hits. Others described gunners engulfed in flames before they could unbuckle harnesses. Lieutenant Masao Sato wrote in his diary after returning from a mission to Espiritu Santo, "I looked back and saw the tail gunner's dome a ball of fire. He did not scream. The flames carried him away in silence." Allied fighters quickly learned to exploit the Betty's weaknesses. F-4F Wildcats and later F-6F Hellcats attacked from below or behind, targeting the wings. A short burst of 50 caliber fire was often enough. In one engagement over the slot on November 11th, 1942, 16 Bettys attempted a torpedo run against American transports. Only 2 returned to base. The rest ignited in midair, their burning fuel forming pillars visible from the ships 60 kilometers away. At Rabaul, maintenance crews worked without rest, patching holes with tin sheeting, replacing wiring burned to copper skeletons. Mechanics called the bomber Hamaki, the cigar. The nickname spread through the fleet, spoken with both pride and dread. Each sortie meant a chance at glory or vaporization. In early 1943, the Betty gained another role: long-range reconnaissance and night attack. Radar-equipped G4M1s shadowed Allied convoys, guiding submarines toward targets. Their endurance was invaluable, but their vulnerability remained absolute. By March, American night fighters equipped with radar were hunting them across the Bismarck Sea. The battle that month, intended to reinforce Lae in New Guinea, turned into a massacre. Allied aircraft destroyed 102 Japanese planes in 2 days. Most were Bettys, their fuel tanks lighting the dark like signal flares. Yet even amid catastrophe, the bomber produced moments of brilliance. On April 18, 1943, a formation of 18 G4Ms departed Rabaul, carrying Admiral Isoroku Yamamoto on an inspection tour. American codebreakers had deciphered the flight plan. P-38 Lightnings intercepted over Bougainville, shooting down both command aircraft. The destruction of Yamamoto's Betty became one of the war's defining moments, a symbol of how vulnerability in design could erase the architect of Japan's greatest victories. Through 1944, the pattern repeated across the Pacific. As Allied forces advanced through the Marianas and Philippines, Betty units shifted constantly, retreating from base to base. Their long range allowed them to strike far behind enemy lines, but few aircraft survived more than a dozen missions. Combat reports from the 702nd Kokutai listed average loss rates of 40% per operation. At Leyte Gulf, modified G4M2s carrying torpedoes launched desperate attacks on American shipping. They achieved a few hits, but were decimated by carrier-based Hellcats. Gun camera footage showed Bettys disintegrating after single bursts, their fuselages consumed by flash fires. Allied observers began calling them one-shot bombers. Despite catastrophic losses, Japanese command continued to rely on the aircraft for roles far beyond its design: mine-laying, transport, even suicide delivery. Beginning in late 1944, the Navy converted several squadrons to carry Oka rocket-powered bombs under their bellies. The concept demanded that the Betty approach within 37 kilometers of Allied ships, release the rocket, and turn away before being destroyed by defensive fire. Few ever returned. Out of 85 Oka missions launched between March and June 1945, 74 carrier Bettys were shot down before reaching release range. The rest vanished in explosions that shook the sea. The bomber's death toll among its own crews was staggering. U.S. intelligence estimated that by war's end, over 2,000 Japanese airmen had died inside burning G4Ms. Pilots learned grim survival rituals, removing gloves to operate emergency hatches faster, keeping side windows unlatched for quick escape, wearing scarves soaked in water to breathe through smoke. Few ever used them successfully. Yet even in failure, Allied respect lingered. The courage of Betty crews was acknowledged in intelligence summaries that described persistent attacks despite hopeless odds. One U.S. Navy report from 1944 concluded, "The bravery of Japanese airmen equals the best traditions of any service. Their aircraft, however, betrays them." By the final months of war, Bettys operated mainly at night, from crumbling airfields on Kyushu and Formosa. Their raids caused little damage, but continued out of duty. Ground observers noted their engines fading into the darkness like the echo of a lost empire. When Japan surrendered in August 1945, fewer than 150 G4Ms remained airworthy. Some were used to carry peace envoys to Allied bases. The same aircraft that had once burned across the Pacific now bore white paint and green crosses of surrender. Mechanics removed their machine guns, polished their wings, and prayed that no Allied pilot would mistake them for hostile. Combat had stripped the Betty of its legend, revealing what engineering reports already knew, that speed and distance could not compensate for fragility. Every fireball over the Pacific traced the same lesson in smoke across the sky. And behind those flames lay a question more complex than strategy: why a nation that could design such beauty had built it to die so easily. The answer would emerge only in the cold arithmetic of post-war analysis. By 1944, the skies over the Pacific had turned against the Betty. What began as a weapon of strategic reach had become an equation in self-destruction. When American intelligence analysts finally compiled performance data from captured aircraft, wreckage, and combat reports, the numbers told a truth too stark for ideology to obscure. The G4M's fundamental flaw was physical, not moral. It carried 4,180 liters of aviation gasoline in tanks made from 1 milliliter aluminum sheet, unsealed and unarmored. At 0.74 kilograms per liter, that fuel added over 3,500 kilograms, more than half the bomber's loaded mass. In flight, the center of gravity shifted constantly as fuel burned unevenly, increasing structural stress on the wings. Under combat conditions, vaporized gasoline filled the fuselage cavity in concentrations between 2.5 and 5%, enough to detonate explosively if sparked. American tests at Wright Field in 1943 confirmed what Japanese crews already knew. A single incendiary bullet from a .50 caliber Browning machine gun ignited the wing tanks in less than 1 second. Aluminum panels melted at 660 degrees, collapsing within 20 seconds of ignition. The resulting fire reached 1,100, sufficient to compromise control cables before the crew could react. Self-sealing tanks, like those fitted to Allied aircraft, would have contained such damage within minutes. But the Betty had none. Comparative analysis with Allied bombers highlighted the chasm between design philosophies. The B-17 Flying Fortress carried 10,600 liters of fuel across 15 rubberized tanks enclosed in protective armor. A single tank puncture rarely destroyed the aircraft. Fire suppression systems and redundant pumps contained leaks. Its empty weight exceeded 16,000 kilograms, more than double the G4M, but survivability compensated for every kilogram. The B-24 Liberator, though criticized for fragile wings, featured self-sealing liners that reduced loss rates dramatically after 1943. In contrast, Japanese data estimated that 86% of all Bettys hit by enemy fire were destroyed by fuel ignition, not structural failure. The math of loss was merciless. In 1942, each G4M required 38,000 man-hours to produce. By 1944, Japan could no longer afford those hours. Aluminum shortages forced substitution with steel fittings that increased weight and reduced endurance. High-octane fuel, rated at 92 octane compared to America's 100-130, limited engine performance and climb. When Allied fighters intercepted at altitudes above 6,000 meters, the Betty's engines lost power rapidly. Combat engineers calculated that the bomber's survivable engagement envelope was less than half that of its adversaries. Japanese after-action reports documented the consequences in grim precision. Over Rabaul, 73% of returning aircraft showed signs of fuel leakage. In 41%, the leaks occurred without enemy contact. Vibration had fractured joints or lines. Maintenance logs described the constant smell of gasoline clinging to airframes, the metallic film left on skin and uniforms. Ground crews nicknamed the aircraft High No Tory, the Firebird, not in reverence but resignation. The decision to forego protection was not ignorance. It was arithmetic imposed by geography. To cross the Pacific from Truk to Guadalcanal required 12,100 kilometers each way, plus reserve fuel. Armor plating and self-sealing systems would have reduced that radius below operational necessity. Engineers warned that Japan's war plan depended on an aircraft that could outrun its own fuel consumption curve. In theory, speed and range would compensate for vulnerability. In practice, Allied radar and interceptors erased that margin by 1943. Field modifications offered little help. Crews wrapped sandbags behind pilot seats, installed makeshift rubber sheets over fuel lines, even filled the space between tanks with seaweed to absorb leaks. None worked. American ammunition, tracer, incendiary, explosive, cut through the thin fuselage like sunlight through paper. Fires spread so fast that gunners rarely reported flames. They simply vanished from intercom channels mid-sentence. Survivors who bailed out described a distinct sound before ignition, a hollow whoomp, like air collapsing into itself. Lieutenant Kenji Tanaka, downed over Bougainville, recalled, "There was no time to think. The airplane became a torch. I fell through fire. Few ever reached the sea alive. Parachutes ignited before opening, soaked in vaporized fuel." For Allied analysts, the phenomenon offered both tactical advantage and moral unease. The ease with which the Betty burned turned combat into slaughter. Fighter pilots reported shooting down entire formations in minutes, each target exploding into a fireball that illuminated the sky. One Hellcat pilot wrote, "You didn't feel triumph, just disbelief that anyone still flew those things." In post-war assessments, engineers translated tragedy into data. They measured penetration resistance, heat tolerance, and burn rate. A B-25 self-sealing tank withstood 7 .30-caliber hits without leakage. The Bettys leaked at 1. American bombers averaged 2% fire-related losses per mission. The Bettys exceeded 30. From these figures emerged a new understanding. Range without protection was a false economy. The loss patterns also revealed strategic decay. As Japan's empire shrank, the distances that once justified such extreme range disappeared. Bases on Saipan, Truk, and Rabaul fell. Operational legs shortened to a few hundred kilometers. The Betty's advantage evaporated, leaving only its weaknesses. By late 1944, commanders openly called it obsolete, but continued using it because no replacement matched its endurance. By war's end, less than 10% of all G4Ms built remained intact. The rest were destroyed in combat, scrapped for aluminum, or consumed by accidental fires. For every bomber lost, 7 trained airmen perished. Total crew casualties exceeded 14,000. Each statistic carried the same cause: unsealed fuel. In the cold precision of post-war analysis, historians recognized the paradox. Japan had built an aircraft that embodied both brilliance and blindness, the pure pursuit of distance achieved through deliberate vulnerability. The Betty was not defeated by American bullets alone, but by the very mathematics of its design. And as engineers at Wright Field completed their final report in 1946, one concluding line captured the essence of that paradox. The G4M was a triumph of range and a failure of survival. It achieved what it was ordered to achieve and perished for it. The numbers could not capture the smell of burning gasoline or the silence of vanished crews, but they defined the boundary between ingenuity and catastrophe. From them, a new generation of aircraft designers would draw the lesson that every kilometer of range must be balanced by the weight of survival. Among the fragments of reports and production data, the most haunting accounts came from those who had lived inside the machine itself. For them, the G4M was not a diagram or a statistic. It was a narrow aluminum coffin that could soar across oceans and vanish in a flash of light. Lieutenant Tetsuo Kuwabara of the 701st Air Group left one of the few surviving diaries of a Betty pilot. His entries from late 1943, written during operations from Rabaul, reveal a mixture of admiration and dread. "The aircraft is beautiful," he wrote. "She lifts effortlessly, like a bird skimming the waves. But when I smell fuel, I think of death. The tanks breathe through the wings, and vapor seeps into the cockpit when we climb. Every man knows what that means." Kuwabara described missions flown over endless sea. The hum of twin engines vibrating through thin panels, the tremor of anti-aircraft shells exploding miles below. Crews developed rituals to calm their nerves. A coin placed under the seat for luck, a silent nod between pilot and tail gunner before takeoff. They called the Betty Hamaki, the cigar, not just for its shape, but for how it burned. His last entry was dated February 1944. "2 of our planes failed to return. They did not crash. They vanished. There is only fire. Then nothing." Kuwabara never came back from the next sortie. For American ground crews who examined the wrecks, the experience was equally unsettling. Sergeant John Finnegan of the 307th Bombardment Group recalled the first captured G4M they inspected at Buka. "It looked like something out of a racing catalog," he said years later. "Every part was polished, thin, precise. We couldn't believe anyone would fly into combat in it. You could dent the fuselage with a thumb." Finnegan remembered opening an access panel and finding the fuel lines running beside electrical cables. "We said to each other, 'No wonder they all went up.'" But the design wasn't stupidity. It was purpose. They built for reach, not return. At Clark Field in the Philippines, another group of American mechanics watched a damaged Betty taxi in after surrender in 1945. The crew had painted large green crosses over the red suns. One of the men, Corporal Tom Bevan, noted, "The pilot bowed before shutting down. The engines hissed like they were sighing. You could see patches over bullet holes, bits of tin nailed like armor. They'd flown this thing thousands of kilometers, with fuel leaking through the wings. It was courage, pure and simple." Even Japanese engineers, when interviewed after the war, spoke with melancholy respect for the aircraft they had created. Kiro Honjo, its chief designer, told American interrogators in 1946, "We knew from the beginning it would burn, but our Navy demanded range above all else. We could not change that. To survive the mission was secondary. We designed for victory, not for return." His voice reportedly broke when he added, "I lost friends who flew it. I think of them every time I see aluminum." For mechanics at Mitsubishi's Nagoya plant, the Betty had been both pride and burden. They worked under the roar of air raid sirens, assembling aircraft by hand when machine tools failed. One worker, interviewed after the war, described the paradox. "We polished each panel until you could see your face, knowing the plane would last one flight. Still, we worked carefully, because to do less felt like betrayal." Among Allied pilots, respect for the Betty's crews often replaced hatred. Captain Raymond Clark, a B-24 commander, wrote in his mission log after witnessing a Betty formation, shot down near Truk, "They flew straight through flak without weaving. The last one exploded so bright it lit the clouds. No one bailed out. They kept formation until the end." For many Americans, these encounters challenged the easy image of a faceless enemy. The destruction of Admiral Yamamoto's G4M, though celebrated as a strategic victory, carried a tone of somber respect even among the pilots who fired the shots. Major Thomas Lanphier, who led the interception, later said, "He was a brave man in a brave airplane. It wasn't his fault his wings were made of gasoline." In the archives at Yokosuka, researchers discovered a final letter written by a Betty navigator, Lieutenant Hiroshi Handa, to his wife in May 1945. The letter survived because it was never sent. It was found folded inside his flight manual. "You will hear that our planes burn easily," he wrote. "That is true. But remember, we built them to reach beyond the horizon. Each flight is a wish to see our homeland safe. If I do not return, think of me as part of the light in the sky." The human voices behind the numbers revealed what design diagrams could not. The faith, discipline, and fatalism that filled those unarmored fuselages. Every Betty carried 7 men bound by trust, stronger than metal, flying a machine that demanded devotion to the point of self-immolation. And when those aircraft finally vanished from the sky, their passing marked more than the end of a model or a mission. It marked the exhaustion of an idea, that courage alone could shield an empire built on fragile wings. When the war ended, the Allied evaluation of Japan's aircraft revealed not only a defeated technology, but a mindset shaped by geography and necessity. The Betty was the clearest expression of that mindset, a machine designed to cross oceans at any cost. To American engineers, it was both a marvel and a warning. The post-war technical analysis conducted at Wright Field and the Naval Air Technical Center in Anacostia went beyond measuring armor thickness or climb rate. It asked a deeper question. How could one of the world's most advanced naval air forces field a bomber so delicate it could be destroyed by a single tracer? The answer lay in Japan's engineering doctrine, which had evolved apart from Western priorities. Since the 1930s, Japanese naval aviation had focused on range as the foundation of power. Japan's island empire lacked forward bases and depended on striking distant targets first. Pearl Harbor, Darwin, Colombo, the Aleutians. Every mission began with the same constraint, the Pacific's immensity. The G4M's design was the natural outcome of that constraint. Its engineers calculated that to achieve a 4,800-kilometer radius, fuel had to make up over half the takeoff weight. Armor and self-sealing tanks were not luxuries they omitted by choice. They were impossibilities under existing performance demands. In contrast, American doctrine grew from continental abundance, large airfields, plentiful fuel, and escort fighters. The U.S. Army Air Forces valued survivability and crew recovery. Self-sealing tanks, redundant hydraulics, and fire suppression were considered standard. Weight was the price of endurance, not the enemy of it. By comparing the Betty to the B-25, Allied engineers uncovered how two nations defined efficiency. The Japanese calculated it as kilometers per liter of fuel. The Americans calculated it as missions completed per aircraft lost. The difference explained the Pacific's aerial tragedy. Japanese test records from 1940s show that engineers at Mitsubishi proposed early versions of self-sealing tanks made from layered rubber and fabric, similar to British designs. The Navy rejected them after range trials showed a 12% reduction in endurance. Strategic thinking overrode tactical reality. Japan's naval leadership believed offense itself was defense, that striking first and farthest would make survivability irrelevant. For a brief moment in 1941, that belief appeared justified. But as the war dragged on, the doctrine collapsed under the weight of attrition. The Betty's destruction illustrated a universal engineering law. Every advantage demands an equal cost. The bomber's low drag, high lift, and immense fuel load gave it unmatched range, but also created an aircraft whose margin of safety was almost zero. A bullet through a fuel line was not damage, it was execution. When American analysts tested the G4M3 variant in 1946, they discovered that even belated improvements failed to resolve this balance. The addition of armor and self-sealing tanks raised empty weight by 600 kilograms and reduced range by 1,200 kilometers. With that loss, the aircraft no longer met its design purpose. It had become, in effect, an ordinary medium bomber, but produced by an industry that could not match Allied quantity. It was the final proof that Japan's original formula could not be corrected without abandoning the reason for its existence. Technically, the lessons of the Betty reverberated across post-war design. Engineers in the United States and Britain studied its aerodynamic efficiency, noting the purity of its lines and the simplicity of its systems. Some design concepts, like the use of integral fuel tanks in wings, would later appear in jet aircraft, though with advanced sealing and fire suppression. Even its failures became valuable data points for the next generation of bombers. To Japan's surviving engineers, however, the lesson was deeply personal. Kiro Honjo and his colleagues testified before Allied occupation authorities in 1946. Their statements, later published in technical journals, read as confessions. "We could not resist the command for range," Honjo wrote. Each meeting ended with the same conclusion: lighten it more, make it go farther. We did not design an aircraft to win a long war. We designed an aircraft to win the first 6 months. American engineers, though critical, acknowledged the ingenuity behind such efficiency. A U.S. Navy report from 1947 concluded, "The G4M represents extreme optimization under severe limitation. Within its parameters, it achieved near-perfect aerodynamic economy. Its destruction stemmed not from poor craftsmanship, but from a doctrine that failed to anticipate endurance warfare." The philosophy of range at all costs was not unique to Japan. German aircraft like the Heinkel He 177 suffered similar issues: overheating engines, flammable fuel lines, and structural compromises in pursuit of performance. Yet the Betty's record made its consequences unmistakable. Between 1941 and 1945, Japan lost over 1,400 G4Ms in combat. Fewer than 1 in 5 missions returned all crews alive. The comparison extended beyond technology to culture. In the United States, engineers served the mission. In Japan, they served the ideal. The Betty's range was not merely a specification. It was a symbol of national willpower, proof that Japanese craftsmanship could reach farther than material reality should allow. That belief endured even as airfields burned and factories vanished. In post-war Japan, when the first civilian airliners took to the sky under Allied supervision, many were built by former Mitsubishi engineers. They carried with them the memory of the G4M's elegance and its cost. Fuel tanks were now armored, firewalls installed, redundancy restored. Survivability had become the new measure of excellence. The lesson had been learned, written in thousands of names lost over the Pacific. In classrooms and design bureaus decades later, Japanese aeronautical students studied the Betty not as a relic of defeat, but as a case study in limits, the point where performance becomes self-destruction. Every nation that built aircraft after 1945 understood this trade-off. The G4M had flown too far to return, but its shadow guided those who came after toward balance. The contrast between the Betty and her Allied contemporaries remains one of the clearest mirrors of wartime philosophy. One side believed endurance was the route to survival, the other that survival was the route to endurance. Between those definitions, thousands of airmen burned, and in the wreckage of the Betty, the world learned that range, untempered by reason, was not power, but illusion measured in kilometers of flame. When the war ended, a few surviving Bettys sat abandoned on airstrips across Japan. Their green paint faded to dull gray, their wings streaked with fuel stains and salt. Allied occupation troops photographed them from every angle, documenting the last echoes of an idea that had once carried Japan's hopes across the Pacific. The aircraft looked elegant even in defeat, slender, balanced, and hopelessly fragile. To the engineers who examined them, they represented both the genius and the delusion of a nation that had chased perfection at the cost of survival. In the months following surrender, technical teams from the United States, Britain, and Australia cataloged each surviving example. At Yokosuka and Atsugi, they disassembled fuselages, weighed components, and traced wiring diagrams. At first, the reports read like autopsies, precise, factual, unemotional. But in the margins, engineers left comments that betrayed fascination. Beautiful workmanship. Impractical, but inspired. Some called it the most efficient bomber design ever made for its weight. Others simply noted, it burns too easily to live. For Japan, the Betty's legacy was inseparable from the nation's transformation after 1945. As industry shifted from weapons to reconstruction, the lessons of the G4M became moral as much as technical. Aircraft design programs under Allied supervision required self-sealing tanks, redundant systems, and strict safety standards. the first post-war Japanese transports built in the 1950s, the Tachikawa and later the NAMC YS-11, bore none of the lightness-obsessed philosophy of the war years. They were heavier, safer, and reliable. Survivability had become a measure of virtue. To aviation historians, the G4M occupies a singular position in the chronology of air warfare. It bridged the divide between pre-war imagination and industrial reality. Before 1939, range defined power. After 1945, survivability defined progress. The Betty's graceful lines and tragic record became a parable of engineering extremes, a case study in what happens when doctrine outpaces resources. American engineers who studied the wreckage drew lessons that influenced post-war aircraft worldwide. The integral wing tanks that doomed the Betty reappeared decades later in jet bombers like the B-47 and B-52, but surrounded by multiple layers of protection and fire suppression. The concept itself was not flawed. Its execution under wartime desperation had been premature. The G4M had pointed the way to the future, but through the wrong war. For Japan's wartime designers, reflection came slowly. In post-war interviews, Kiro Honjo admitted that he could never bring himself to visit the sites where his aircraft had burned. "I thought of them as my children," he said. "I gave them wings that were too light." His confession became part of the larger reckoning within Japan's engineering community, a recognition that technology without endurance serves only destruction. Among Allied veterans, memory of the Betty carried a strange respect. Pilots who had fought against it described its speed and silence with admiration. Some said they had never seen an enemy aircraft fly so gracefully before disintegrating. Others remembered the courage of its crews who pressed torpedo runs through curtains of fire, knowing any hit would ignite them. To many Americans, the Betty symbolized not fanaticism, but fatal devotion, a machine flown by men who obeyed design as destiny. In museums today, only a handful of restored G4Ms remain. Their wings stretch under soft lights, polished again to their original shine. Visitors walk past placards describing range, speed, and payload, unaware that every figure on those displays represents a trade for lives. Behind the glass, the rivets still glimmer, perfect and thin. The beauty endures, even as the logic that created it has long since vanished. The final chapter of the Betty story came not from engineers or pilots, but from a single flight at war's end. On August 19, 1945, two G4Ms painted white with green crosses lifted from an airfield near Tokyo, carrying Japanese envoys to the surrender conference in the Philippines. Their engines droned steadily over the Pacific, the same route that once led to conquest. American fighters escorted them peacefully to Ieshima. When the bombers touched down, one of the pilots reportedly whispered, "We have reached our limit." That flight closed the circle. The aircraft born to carry war across oceans now carried peace. It arrived unarmed, unarmored, yet alive, the last surviving expression of a philosophy that had consumed itself in flame. Historians often describe the G4M as a failure, yet in its failure lies its meaning. It proved that brilliance divorced from realism leads not to victory but to waste, that lightness without protection is not efficiency but denial. The Betty's elegance was the reflection of a nation's will, its destruction the consequence of refusing balance. Long after its last engine fell silent, the lessons remained. Every modern aircraft that trades speed for protection or efficiency for endurance carries within it an echo of the Betty, a reminder that progress measured only in distance will always end in fire.